Hello and welcome to the Unit 4 podcast on section 11.4. Today we're going to be talking about empirical and molecular formulas. I'm Mr. Sakaguchi.
And I am Mr. Lin.
And let's start. So percent composition is basically looking at the percent by mass of an element in a compound. So we can basically calculate percent composition simply by looking at chemical formulas. For instance, if we took water, the percent of hydrogen in water is we have 2 moles of H, and then the denominator would be the entire mass of the water compound. So if I multiply 2 times 1.01, the 2 comes from the fact that there's a 2 in the formula, by the way. The 1.01 comes from the periodic table. I didn't happen to round this 1 to 1 in this case. So that, and then we have the molar mass of water. At this point, I'm assuming you know how to calculate molar mass. It would be 2 times H plus the weight of O. That's where the bottom comes from. You multiply by 100%, you end up with 11.2% for hydrogen. For the oxygen part, it's the mass of 1 mole of oxygen divided by the molar mass of water. Again, because there's nothing in front of O in the formula, that's why it's only 1 here. And then again, the molar mass as you saw for hydrogen. So 16 over 8.02, 18.02 gives us 88.8% for oxygen. So sometimes it's important for us to know how much percentage of a compound, of an element there is in particular compounds.
It actually becomes more interesting when we do the exact opposite, which we'll show you a little bit later. It's a pretty big thing in chemistry, actually.
Empirical formula is the definition is the whole number, smallest whole number ratio for a compound. This may or may not be the actual formula of the compound. And this is something Dalton did back in his time. Despite not having any idea of what moles were, he was able to find ratios that he was able to make empirical formulas for. Molecular formulas are very similar to empirical formulas, but they're always multiples of the empirical formula.
And we'll show you the difference between empirical versus a molecular formula and how to find out.
So I have an example here. So for instance, HO, this would be the lowest whole number ratio, so this would be the empirical formula, whereas H2O2, notice that if we divided both of these by 2, we would get the empirical formula. This is a multiple of the empirical, so this is what we call a molecular compound. So basically we're going to ask ourselves, how do we do these kinds of problems? So there's a very simple strategy for solving for empirical formula. The basic, what we do first is we take our percentages that are going to be given to us and we convert them into grams. Then what we do is we do our conversion from grams to moles by dividing by the molar mass of the elements that make up the compound,
which you find on the periodic table.
Then we make mole ratios by dividing by the lowest total moles for whichever element that happens to be true for.
So since there's multiple elements, you're going to have multiple different numbers. You're just going to pick the smallest one. You're going to divide all of them by that small number, which is going to give you a new decimal.
Now hopefully after you make these ratios you're going to have whole numbers, but if you don't, usually you're going to end up with very simple decimals that are akin to very simple fractions, so like 0.25 for a quarter,
0.5 for half,
0.333 for a third. And when you have these, we eliminate these by multiplying by, well, for 0.25 we'd multiply by 4, 0.5 we'd multiply by 2 to eliminate the decimals, ending up with all whole numbers.
And that will pretty much give you your empirical formula.
Yeah, the whole numbers will make up the subscripts in the formula.
Right.
So here's an example of how we would do this. So let's say we wanted to find the empirical formula for methyl acetate. So these are the percentages of C, H, and O that make up the methyl acetate. So the first thing we would do is we would drop the percentages and change them into masses. So essentially what we're doing here is we're assuming that we have a 100-gram sample of this compound. Then what we do is we multiply by 1 mole over the molar mass of C, H, and O to go from grams of each individual element into moles.
Right, so this is to simplify the molar ratio of what's going on.
And so now we have 3 different mole values for carbon, hydrogen, and oxygen. So what we're going to do is we're going to look at these 3 mole values and we're going to divide everything by what's least. So if we look at these 3 numbers, the lowest mole value is going to be the 2.700 moles of O. So what we're going to do is we're going to divide everything by 2.700. when we do this, we end up with some numbers here. So when we, obviously the first one you're going to get a 1 for dividing O by itself. We get 3 for hydrogen, but notice how we get 1.5 for carbon. So here's an example of where this is one of those decimals that come up. Now remember, for empirical formulas everything should be a whole number. So to get rid of this 0.5, the easiest thing to do would be to multiply by 2. Now when we multiply by 2, we can't just multiply the 1.5, we multiply everything by that factor. So if 1.5 gets multiplied by 2, everything else gets multiplied by that same number.
Which gives us an entirely new ratio of a 3:6 to 2. And when we write it out,
so the simple whole ratio is 3 moles of C to 6 moles of H to 2 moles of O. So the empirical formula would be C3H6O2. Now it doesn't really make a difference what order you write it doesn't matter whether the H comes first or the C. As long as you get these little numbers correct is what matters.
right.
Now for molecular formulas, this is basically when you have the same percent composition and the same empirical formula. So the simplest whole number ratio doesn't always indicate the actual compound.
Because sometimes you wind up with a substance where you've got a molar mass. 1 mole of the substance weighs more than just the empirical formula would show. So that means there's an alternative or a different ratio that's involved, and it deals with multiples.
Right. So for instance, carbohydrates have an empirical formula CH2O, and a lot of like glucose and ribose and deoxyribose would all have
The same ratio.
Would have the same percent composition, the same empirical formula.
Right.
So this is where molecular formulas come in. So we have the molar mass. We need to know the molar mass of the molecular formula to tell us what we need to multiply the empirical formula by in order to get the actual mass of our molecular compound. This is the way we're able to tell what kind of carbohydrate we have in a particular sample, for instance. To kind of illustrate this, let's say we have acetate and the molar mass is this. Okay, we know that the empirical formula, which is CH, is this. So we can use these to figure out what the molecular formula is. So what we want to know is what to multiply by. So we take our molar mass of our molecule and we divide by the empirical molar mass. We should end up with a whole number. So we actually do this, we end up getting 2. This one's kind of obvious. So the molecular formula is actually 2 times
Our empirical formula.
Empirical formula. So this becomes C2H2.
That's it.
That's it.